Hello, I will start the final exam presentation from now on. The table of contents is as follows. First, band pass filter concept and ADS design. Second, RNA concept and ADS design. Band pass filters using RC components are used in several radio frequency applications. These filters enable a band of frequencies to be passed through the filter, while those in the stopband of the bandpass filter are rejected. Cascading the low-pass filter and the high-pass filter, a bandpass filter can be obtained. Like the high-pass filter and the low-pass filters, there are two topologies that are used for these filters, namely the pi and the T configurations. These resonant circuits are either series or parallel tuned RC circuits. We design T-format bandpass RC filter by ADS. We set the cutoff frequencies for the bandwidth 4.4 GHz to 4.8 GHz. So a low-pass filter inductor is equal to 1.657 nanohenry, and at the high-pass filter, capacitance is equal to 0.724 picofarad. So we construct the bandpass filter circuit like this. This part is low-pass filter part, and this part is high-pass filter part. So we can construct the bandpass filter, and with simulation and verify the circuit. The parameter, the S parameter 2.1 is the gain response, and S parameter 1.1 is the return loss. This is the LNA concept. The LNA is low noise amplifier. LNA is normally placed at the first stage of RF receiver because it promotes the low noise performance of receiver. Input 50 ohm matching is also important due to matching with the antenna or RF filter. This is the content of RNA necessity. First, the NF and the gain in the first stage have the greatest impact on the NF in the overall system. Second, the biggest influence in determining the sensitivity of the system. Third, the mixer has a very high noise figure, approximately 10 dB. Finally, if the mixer's NF is very low, about 2 dB or less, LNA is not required. And we concept the convergence circuit. Input convergence is configured to satisfy pi's single equal gamma optimization with minimal noise figure. Conjugate matching for maximum benefit with output convergence circuit. Trade-off needs between noise figure and gain. Configures balance structure to improve VSWR. At DC bias point, for the design of an amplifier, we use the ADS model. ATF/54143 is the noise index is 1.3 dB, and the overall gain is 23.4 dB, enough to meet the desired conditions at 900 MHz, and VDS equals 3 volt, and current DS is equal 16 milliampere. A VDS equals 3 volt, and the current DS equals 16 milliampere in accordance with the bias condition in the datasheet, VGS operates at 0.57 volt. A circuit to facilitate the composition of each circuit, the gate side, the drain side, the source side, and APF /54143 were divided into blocks. As seen in the preceding noise factor characteristic, the noise figure depends on the matching of the input terminals. Therefore, low noise matching of the input terminals is required. At the gate part, this block was used to prevent this from entering the input, and 4.9 nanohenry inductor was used to prevent RF signals from flowing into the bias. In addition, 1.5 nanohenry inductor was used to hold the area where the noise was minimal. At drain part, the output side simply used this block to prevent this from entering the output and attached a resistance of 7 ohms for stability. At source part, for stability, a resistance of 5 ohm was attached and grounded through a capacitor of 0.6 picofarad. As stability, all of them went out of the concentric circuit to show unconditional stability, and the stability index was also above 1. At noise figure, the noise index was found to be 0.567 dB at 900 MHz, meeting the requirements. The noise figure is now affected by the matching of the output. Therefore, the matching of the output stage results in a conjugate match that can achieve the maximum gain. At drain part, for output side matching of capacitor of 6 picofarad and the inductor of 7 nanohenry were added. As stability, all of them went out of the concentric circle to show unconditional stability, and the stability index was also above 1. Again, the gain was 20.7 dB and 900 MHz, far exceeding the 18 dB expected and meeting the conditions. At noise figures, the noise index was found to be 0.567 dB at 900 MHz, meeting the requirements. This shows that the noise index does not change by output side matching. At impedance matching at 900 MHz, you can see that both S parameters are approaching 15 ohm. In conclusion, we have met the initial conditions, and it is important to trade off noise gains. For input matching, it is recommended that you match the point where the noise figure value is minimal. And it is important for output matching to match the conjugated values of S parameter 22 as matching points. The reference are as follows, and thank you very much.